Today we're very happy to have Alex Maloney, who will be telling us about quantum cosmology in 2+1 dimension. And before we start, we are going to close the webinar, but not today, but tomorrow. Everyone is invited to come, and please send an email to Lisa if you plan to come so that we can make the reservation.
Good. So it's great to be back, as always. So today I'm going to talk about some attempts to make sense of quantum cosmology in a low number of space-time dimensions. What I'll be talking about today is mostly based on two papers, one of which came out over the summer, another of which is to appear hopefully shortly. Both of these are in collaboration with Joydeep Chakravarti, postdoc at McGill, who's looking for postdoc positions this year. Keva Namju, a student at McGill, also looking for postdoc positions, and Simon Ross at Durham, presumably not looking for postdoc positions. I am also not looking for postdoc positions, although I don't know, make an offer, we'll see. And as always, let me just please encourage anyone to interrupt, stop, and ask questions if anything at any point could use some clarification. So I'd like to begin just with a very general overview. So quantum cosmology is, of course, very confusing. Some of the questions that we might like to try and understand are questions about, for example, what Hilbert space of states one should use to describe the possible configurations of the universe. One might like to understand what principle picks out the state of our universe. Maybe it's a Hartle-Hawking prescription or something else. And finally, how might we interpret the entropy of a cosmological event horizon? And of course, the ADS-CFT correspondence is a great tool to answer questions in quantum gravity, but previous attempts to try and apply it in cosmological settings have run into some sort of confusions and obstructions. And what we really need, I think, are some sort of simple, solvable models where we can try and make precise statements and unpack some of these difficulties. Now, the sorts of theories that I'd like to consider today are theories of gravity in 2+1 dimensions. And so here, today, I'll be thinking entirely about pure gravity, although not entirely about pure gravity, I guess I should say, but mostly about pure gravity, by which I mean three-dimensional general relativity with a cosmological constant. And I'll have things to say about both sides of the cosmological constant. And of course, in general, we might add some boundary terms, such as a Gibbons-Hawking boundary term that I've written here, or in a holographic context, we might also want to add holographic counterterms. Now, 2+1 dimensional general relativity is a relatively simple theory. It has no propagating degrees of freedom. There's no local graviton, but there's still a sense in which it has global degrees of freedom, which is to say degrees of freedom associated either with the presence of a boundary or with some non-trivial topology. And because of that, I think it is, you should think about three-dimensional general relativity as something closer to a topological quantum field theory or a quantum mechanics theory with fewer degrees of freedom than one might have in a more complicated theory of gravity. But nevertheless, there's still non-trivial cosmological solutions with both signs of the cosmological constant, positive and negative. Now, in the past, a lot of work has been done on trying to make precise ideas related to quantum gravity for 2+1 dimensional general relativity. Most of the work in the past is focused on Euclidean quantities. So for example, a typical thing one might compute in Euclidean signature is something like the partition function of the theory, which would be an integral over Euclidean manifolds. So here I've sort of schematically written down the sort of thing one tends to compute in Euclidean signature. So one fixes some boundary data. So here I'm imagining you might have some surface off at infinity, and then you might sum over three manifolds that fill in that surface, whose boundary is that surface, weighted by an appropriate Euclidean action. And you might try and compute such a Euclidean partition function by doing something like summing over saddle points. The saddle points would be solutions of the Euclidean equations of motion. And then if you're very powerful, you might include perturbative corrections, loop corrections, and stuff like that. And you might try and make such a Euclidean path integral precise. And there's been a great deal of work, some of it more successful than others, in trying to do so. Today, however, in our study of cosmology, what I'm going to be trying to do, with a limited degree of success, is consider Euclidean, Lorentzian path integrals rather than Euclidean ones. And our main inspiration, our main motivation, which will be guiding us as we try and do so, is the really amazing calculation of Saad, Schenker, and Stanford, who took a sort of Lorentzian point of view, a Lorentzian path integral point of view, when they were studying the spectral form factor. So in that work, what was considered was the two-point function of the density of states. So here I'm considering a partition function, trace e to the minus beta h plus iht, and I'm looking at its square, its absolute value squared, and trying to study that by thinking about it as a sum over geometries. Now, one geometry that would contribute, so here we're considering the thermal partition function, say, of a conformal field theory. And of course, at high temperature, the thermal partition function of a conformal field theory can be computed in ADS-CFT by looking at a corresponding black hole in anti-de Sitter space. And so one could just take two of those black hole solutions, that's some disconnected geometry that contributes to this spectral two-point function, which is essentially the two-point function of the density of states. And of course, that is one contribution, and it's a disconnected contribution that factorizes. But there's a different saddle point that dominates at much larger values of this time coordinate here. That's known as the double cone. And the way that one thinks about this is one periodically identifies in Lorentzian time. So you take a single ADS black hole, you periodically identify in Lorentzian time. And then this saddle point gives a contribution to the spectral form factor that grows linearly in time. Roughly speaking, the action is zero of that saddle point, but it has a linearly growing one determinant. And this reproduces various features that are expected to appear in chaotic theories. In particular, as we'll review in a little bit more detail later, that linearly growing in TPs reproduces the repulsion of eigenvalues that one expects in a chaotic theory. And so what I'm going to be doing today is I'm going to be inspired by this calculation. I'll write down some similar sorts of saddle points that instead have interpretations in terms of cosmology. And then we'll see how far we can get.
But do you have a random matrix?
I'm going to be focusing almost entirely on the bulk perspective. Randomness will appear. I don't have random matrix theories. So in JT gravity in 2 dimensions, the boundary theory is roughly speaking a random matrix theory. Here I'm in 1 higher dimensions. So one should really think about a random conformal field theory rather than a random matrix theory. A lot of the work that has been done on the computations of Euclidean path integrals like this in Euclidean ADS-3 gravity with a negative cosmological constant can be interpreted in terms of random conformal field theories rather than random matrix theories. I'm going to be going a slightly different direction, but we'll talk about random conformal field theories in a little bit as things proceed. I'm happy to talk about that separately, though, if you're interested. Good. Okay. So let's start by thinking about cosmology with a negative cosmological constant. So let's just begin by remembering a few things that we may or may not have learned about this double cone saddle point. So if you have a chaotic theory, then typically there's a level repulsion in the sense that if you look at the density of states, rho of E, and you look at its two-point function, then one way that you can think about level repulsion is that there's some sort of repulsive potential that prevents eigenvalues from being too close to one another. And if instead of talking about the density of states, you were to talk about, say, a partition function trace e to the minus beta h, then you're taking a Fourier transform of 1 over delta E squared, and you get a contribution to the two-point function of the density of states, known as the spectral form factor, that grows linearly in T. And in the context of 2 + 1 dimensional gravity, the saddle point, the Lorentzian saddle point, that contributes this linearly growing piece to the 2-point function of the density of states is the 2 plus 1 dimensional version of the double cone. And just to say things a little bit more explicitly, what is that geometry? That geometry is the ADS black hole, so the BTZ black hole, whose metric I've written down here. I'm writing it down in slightly unusual coordinates just to set the stage for what I'll be doing shortly. U here is a radial coordinate. We have standard time and angular coordinates. The horizon of the black hole is at U equals 0, where the coefficient of dt squared shrinks to 0 size. And in the double cone, we are computing trace e to the minus beta h plus iht. So you have a Lorentzian time translation. And so that means that you periodically identify with period capital T. So little t here is a global time coordinate, and capital T here is the periodicity of that Lorentzian time coordinate that you impose in order to get a contribution to the spectral form. And roughly speaking, this geometry has 2 boundaries. At U goes to plus infinity and U goes to minus infinity. And because it has 2 boundaries that are periodic with period capital T, it gives you a contribution to the spectral form factor. And one piece of the one-loop determinant of that geometry gives you this linearly in T growing mode. Now, if you dig into the literature and you actually read these papers on the spectral form factor, actually what they compute is not the canonical ensemble partition function, but rather a microcanonical partition function. For our purposes today, we don't, I think, need to worry too much about the details. But when I write down results on the next couple of slides, I'll actually write them down in terms of this microcanonical version of the partition function. So you should think of this as a partition function not evaluated at fixed temperature, but at fixed energy, where you're considering some window of states around some fixed energy, and you're thinking about it as a function of Lorentz. So this is the 2 plus 1 dimensional version of the double cone, and it contributes to the spectral form factor. Its action you can compute at 0, so you get an e to the 0 from the classical action, and the one-loop determinant is linearly in T. Now, of course, there are several confusing things about this geometry. So first of all, I used to be very scared about geometries like this, which had closed time-like curves. That's one reason to be a little cautious. But another reason to be cautious is that this geometry is singular at U equals 0. So in the original BTZ geometry, U equals 0 was the event horizon. But now we've periodically identified this event horizon, this time coordinate. So I have a time circle that's shrinking to 0 size. And so you have a singularity at U equals 0, which when you try and do computations can lead in principle to all sorts of problems. In the cosmology language, this singularity at U equals 0 is essentially what people call a known singularity. So one way to proceed is to try and modify your solution a little bit in such a way as to avoid that singularity. And the way that has been adopted in the literature is to complexify the geometry. And here is how we're going to complexify that geometry. So what we're going to do is make a change of coordinates. So essentially what I'm going to do is instead of taking U to be a real number, which is my coordinate, I'm going to take it to be a complex number. So I'm going to take it to be a function of some real coordinate. Rho is now my coordinate of the space-time. And I'm going to choose some complex contour, U of rho, through the complex U plane. And then I'm going to consider this metric. But what is this metric? This metric is exactly the same as this metric, but with a change of coordinates where you let U be some function of rho. The only subtlety is that it's now allowed to be a complex function of rho rather than just a real function of rho. But this complex geometry, because it's related to our original geometry by a change of coordinates, still satisfies the equations of motion. But because U is complex, it's now a complex metric. And if you look, for example, at the original paper of Saad-Schenker and Stanford and some of the follow-ups to that paper, what they did is they avoided the singularity at u equals 0 by taking some contour in the complex U plane that avoids the singularity. So for example, you can go right above or right below the singularity at u equals 0. Okay. Now, of course, there are still rules to this game. And you might ask, well, am I allowed to think about any arbitrary complex metric? And the answer is not quite. So for example, you might want, in order to interpret a geometry as a legitimate saddle point of your equations of motion, you might want perturbative fluctuations of fields in that background to be well-defined. And there's this very nice criterion of Kontsevich and Siegel, later clarified and sort of worked out in some examples by Edward, which is a condition that one can impose on the complex metric, which essentially is the condition that if you study perturbative fluctuations of fields in this background, you just take free fields in this background, the perturbative fluctuations are Gaussian integrals, and you want all of them to be right sign Gaussian integrals rather than wrong sign Gaussian integrals. And so I don't want to go into too many of the details of how we impose this condition, except to say that the complex contours that I'll be writing down for you in a minute are specifically chosen to satisfy this condition. And indeed, if you want to try and interpret this condition, you could just stare at this. So what am I doing? I'm focusing on a diagonal metric, such as the one that I wrote down for you here. And I'm demanding that the arguments of the coefficients of that diagonal metric sum up to a number that is less than pi. So for example, if you have a Lorentzian geometry, one of those arguments is pi, because you got a -1 signature, and the rest of the arguments are 0, because they have +1 signature. And so, for example, a purely Lorentzian metric doesn't quite satisfy this condition, because the sum of the arguments is exactly equal to pi. On the other hand, a Euclidean geometry, of course, the sum of the arguments is equal to 0. So you should think about this criteria as sort of making precise the notion that if you want a complex geometry to be viewed as a saddle point of equations of motion, you need to make it slightly Euclidean. You need this to be slightly less than pi. Good. Any questions? Yeah.
Sorry, I'm probably misunderstood. So with the purely Lorentzian doesn't obey this, but we still know that perturbative field theory makes sense.
Sure, but that means that when you study perturbative field theory and Lorentzian signature, you need to work a little harder in order to understand exactly what you're doing. So
It's
you
like
might need to impose.
sufficient, but not necessary.
This is one possible criteria. I wouldn't necessarily call it necessary.
Well, you could say that the Feynman I epsilon
Exactly,
fixes it.
exactly.
Pushes it down.
Yes.
Yeah, yeah. So in Lorentzian signature, you need to be a little careful. You need to decide exactly what it is you're computing. And for example, the I epsilon prescription is in a sense, a way of making that prescription. Okay. Any other questions, comments? Great. Okay. Now let's go ahead and revisit the geometries that I wrote down for you earlier. Okay, so here was our complex geometry. Okay. So we have sinh squared u, cosh squared u, and u prime squared, t rho squared. Now, our original double cone was just taking u equals to rho, okay? That was the original BT solution. And of course, now with the benefit of hindsight, really what you might want to do is take u equals rho plus I epsilon to go slightly above that singularity at u equals 0 in the complex plane. But as reviewed, that contributes to a spectral form factor. But then let's go back and look at this formula for the metric again. So another thing you could do is you could take rho, u, to be I pi over 2 plus rho. What happens when you do that? That minus sinh squared becomes plus cosh squared. This plus cosh squared becomes minus sinh squared. And you get exactly the same BTZ geometry back again, except t and phi have switched roles. So what we see is that in this case, there is a different kind of double cone that contributes. That is a Lorentzian saddle point. If the original double cone is a legitimate complex solution, then this is an equally legitimate complex solution, except that the role of T and phi has been reversed. And this is also geometry that has two boundaries, each of which is a torus, is a Lorentzian torus with a periodically identified time-like coordinate and an angular coordinate. And so this also will give you a contribution to the spectral form factor. In order to understand what sort of contribution it gives, we have to do a little bit of thinking, which is always dangerous. But essentially what we need to notice is that now T is playing the role of an angular coordinate, and phi is playing the role of a time coordinate. Phi is periodically identified with period 2 pi, and T is periodically identified with period capital T. So if you want to go back and compare that to your original spectral form factor, what you need to do is you need to do a conformal transformation that rescales phi and T by some amount. And you also need to, it turns out, if you go through the details, rescale the horizon radius of the black hole by an amount capital T. And so if you just trace this through, what you find is that this is another geometry, just as legitimate as the original double cone, that also contributes to the spectral form factor, but it contributes to something slightly different. It contributes with a 1 over T rather than a T, because I had to because my phi and T coordinates switch roles. And it contributes at a slightly different value of the energy. So it contributes to the spectral form factor, but with a slightly different set of parameters. Finally, and really this is the thing that I wanted to focus on today, there is a third contour that I could take through the complex plane. And it's the one where you take U to be I times rho. In that case, this becomes plus sine squared, this becomes plus cosine squared, and this becomes minus d rho squared. So now what was the radial coordinate is playing the role of a time coordinate, and we have a cosmology that looks like this. Okay? So this is a big bang, big crunch cosmology, where the spatial slices are a torus. So if you wanted to draw a picture of it, it looks something like that. It's got a big bang and a big crunch. And at the big bang, let's see, the T cycle shrinks to 0 size, and at the big crunch, the phi cycle shrinks to 0 size. And, you know, this shouldn't be such a surprise. I mean, I think we all know that if you go behind the horizon of a black hole, you find something that looks like a cosmology, where the radial coordinate of the black hole plays the role of a time coordinate. That's what we're doing. The distinction is that for a black hole, the time coordinate is not compact. So it's not a cosmology with compact spatial slices. Now, when we think about the double cone, suddenly this is a cosmology with compact spatial slices. And so what happens when we try and complexify these geometries to avoid those Milne-type singularities that we referred to earlier? Well, you actually find something rather surprising. So here I'm drawing the contours in the complex U plane that you get when you try and avoid these singularities. So this is the real U axis. That's the original double cone, where I just added a small imaginary part to the double cone. Okay. This is the dual double cone, where U is I pi over 2 plus a real number. So that's this contour. The original black hole event horizon is right here at the origin. This is what is basically the black hole singularity, okay, at U equals to plus I pi over 2. And here's my cosmology, okay? It's that contour here, right? So the cosmology behind the event horizon of a black hole sits between the horizon and the singularity. But what happens, and this is the non-trivial calculation, is that when you try and complexify the geometry in order to avoid violating this Kontsevich-Siegel condition, what you find is that your cosmology grows whiskers, okay? So that this cosmology, you know, it sits between here and here, but instead of hitting the singularity here, one glues on a slice that looks like the outside the horizon region of a BTZ black hole. And over here, you glue on a slice that looks like the outside the horizon region of the S dual of the BTZ black hole. Okay. And essentially, this is forced on you if you want to satisfy this Kontsevich-Siegel condition that all of the field fluctuations are right sign Gaussians rather than wrong sign Gaussians. What does this mean? This means that our cosmology, once we add this tiny complexification, also contributes to the spectral form factor. Except it contributes to the spectral form factor with one part that looks like the original double cone and another part that looks like the S dual of the double cone. And you can go ahead and compute the classical action at 0, just like in the Sodden-Schenker-Stanford calculation. You can look at the one loop fluctuations and it grows linearly in T, just as in that previous case. The distinction is that first of all, you have a T and a 1 over T here. But more importantly, I think for our perspectives, is that this is describing a contribution to the 2-point function of the density of states at different values of the energy. Okay. Remember, the original double cone described a contribution to the 2-point function of the density of states at nearby values of the energy, right? It described things like level repulsion in some small region of the spectrum. Now what we're discovering is that this cosmology gives a contribution to the 2-point function of the density of states in different parts of the spectrum. Good. The thing that I would like to advertise, though, and the challenge that I want to present to the audience, is that now we have a relationship between a cosmology, a genuine, closed compact universe cosmology, and a completely vanilla object in two-dimensional conformal field theory, right? What could be more straightforward than the density of states of a two-dimensional conformal field theory? And so the claim is that there's a particular 2-point correlation function of the density of states in a conformal field theory that computes for you the amplitude for this closed universe, Big Bang, Big Crunch cosmology. And this is a quantity, cosmology is mysterious, quantum cosmology doubly so. But this is a quantity here on the left-hand side of this equation that is completely well-defined in any unitary conformal field theory or ensemble of conformal field theories. Okay, and so the challenge to the audience is compute this in your favorite family of conformal field theories, your favorite disordered chaotic conformal field theory, and see if you get this answer that we predict. Yes, please.
Forgetting conformal field theory for a second, just in chaotic quantum systems, do you expect this linear in T growth?
Yeah, so the linear in T growth is something very, very universal in any chaotic system. You can see it, for example, from the Guthweiler trace formula.
Now with this T dependent E prime, I thought, or it's not as, or is it? Clear?
Well, it depends. Yeah, so if you, maybe I'm not quite sure.
Is this, I guess my question is just, is this linear in T growth something like a feature of chaotic systems, just like the linear in T growth?
So, okay, good. So first of all, if you try and do this in one less dimension, there's no analogous clear result. It was really important that I had both the regular double cone and this S dual, what I call the S dual double cone, where phi and T switch roles. If I don't have a spatial direction that can switch roles with a time direction like this, then I don't have any simple analogous result. So this is something that I expect only in conformal field theory, not in sort of random Hamiltonians or random matrix theory.
But I can define these quantities in any.
You could define these quantities, but I wouldn't expect this behavior.
Okay, yeah, that was my question.
Yeah, good, thank you.
We could still have an L to Z generalization of this.
There are many generalizations, which I'll talk about momentarily. Okay, good. I didn't do all the generalizations in our original paper because you can't do everything in your original paper. You'll never get any citations. Okay, good.
Right.
when you call it S duality, do you mean S in the sense of SL2Z?
I mean,
Or S in
S,
the sense of S duality?
I mean, S in the sense of SL2Z, which to me means, you know, if I have a 2D CFT with the Euclidean, well, usually it's talked about Euclidean signature with a Euclidean T, time, direction, and Euclidean phi, you flip them, right? That's all I mean. I'm not saying anything fancy. There's nothing too fancy. Yeah. Good. So, yeah. Okay, so let me just end this portion of our discussion with some words about interpretation. Okay. So first of all, one of the things to note, as I emphasized earlier, is this is a contribution to the 2-point function of the density of states at different values of the energies. Okay. So let's think about what sorts of regimes we might want to investigate this formula in. One thing you could do is you could take large T with fixed E. Okay. So that means that here you're studying some, you know, heavy states, some black holes in the theory. In the CFT language, these would be states up in the Carty regime of the density of states. And E, on the other end, if you fix E prime, E is going to 0. Okay. But remember, we're in 3D gravity, 2D CFT land, where E going to 0 doesn't mean you're studying the vacuum state of the theory. It means that you're studying states which in the CFT language have dimension very close to C/12. Okay. So in particular, in the conformal field theory language, what we're doing is we're probing the 2-point correlation function between heavy states, states in the Carty regime, and states with dimension of order C/12. This is a sort of famous regime in 2D CFT language. It's known as the enigmatic regime to the cognoscenti. In particular, if it's the regime where the density of states is not Carty, but it's also not constrained by the S transform of Carty. And again, I mean S in the sense of the SL2Z modular invariance of a 2-dimensional conformal field theory. So in other words, the information about this closed cosmology is encoded in 2-point densities of states between states right near the Hawking page threshold and heavy states. Now, if one were to take this a little bit more seriously, one could remember, well, heavy states are related by modular invariance to light states. That's a core feature of 2-dimensional conformal field theories. So alternately, I could describe this as a statement about the connected correlation functions between light states, states with dimension small compared to the central charge, and states with dimension of order the central charge. And for those of us who think about 3-dimensional gravity, you know, there is a sort of famous observation due to Edward, which is that one can think about a conformal field theory dual to pure gravity as one which possesses no non-trivial light states. The only light states in the theory are the identity operator and the Virasoro descendants of the identity operator. Because the correlation functions between the identity operator and all of its descendants and the other primary states in the theory should factorize, you might think this means that pure 3D gravity does not exist. I think that's far too strong a statement to take from what I've described to you so far today. Instead, I might take it to mean that if pure 3-dimensional gravity exists, it is probably not the kind of chaotic theory where one would get a contribution to the 2-point function of this type. And of course, as I alluded to before.
Could we go back to the last?
Sure, please.
I wouldn't have thought the chaotic theories have correlations between levels of different energies.
Well, generically, I don't know of any generic reason to think that they do. But the gravitational saddle point that we've described makes a prediction for a certain class of correlation functions between states at different energies related in this way. But of course, this is not something that we expect for generic random matrix theory. because this is not something that we can derive in JT gravity or in two-dimensional gravity. This is a prediction for the correlation functions between states at different energies in two-dimensional conformal field theories, not random matrix theory. Great. Any other questions? Okay.
In summary, the relations between the energies implied by modular invariance and consistency conditions.
This does not follow from modular invariance. Initially, initially I thought, oh, maybe the correlation. So there are sort of trivial. There's the 2-point function of the density of states, E with E that you get from the double cone. Then modular invariance relates heavy E to light E. Okay. So there's also a 2-point correlator between light states and heavy states that's implied by the double cone plus modular invariance. This is a different thing, which is a 2-point correlation function between intermediate states and heavy states, or intermediate states and light states. It's not, as far as I can understand, implied by modular invariance.
I didn't understand your discussion of light states, because isn't this formula valid only when T is large enough, and so the E's have to be large enough?
Yeah, so you have to be a little careful here. This should be valid when T is large, but not too large, I think. Or else you get into a plateau-like regime.
Sorry, by light you mean delta C/12 or less than C/12?
Light means less than C/12. So these two sentences here are just this expression. And here I'm sort of making a moral point that if I take this guy, or sorry, I guess it was this guy to be heavy, I could always just by modular invariance relate that to the spectrum of the light stuff. Okay.
But in this formula, wouldn't light in the sense of less than C/12 mean this is negative?
Right. So I'm skipping a couple of steps in the logic here. So first, let's imagine that this guy is E is of order E is close to 0, meaning delta is close to C/12. And this E is bigger than C/12 by some big amount. Then I do the modular transform of this bigger than C/12 to make it much less than C/12. And so this is now a correlator between much less than C/12 and of order C/12. Is that, this is really a speculation. I don't know. I mean, I don't know how seriously one should take that.
But couldn't you use the similar logic if you just look at, I don't know, something like the usual spectral form factor, interpret it as correlations between some heavy operators with some other heavy operators? And you can say, well, both of those are heavy, so it's like it's equivalent to connected correlators between light operators and light operators.
Sure, and people have written papers on. There's a paper by Christian Jensen, I believe, on
but I'm a little confused. Wouldn't you say that, well, there aren't any light operators, so it's factorized because it's just the two vacuum blocks. So sort of the same contradiction.
Well, I mean, I think it's a connected contribution, so it's exponentially small. So yeah, I don't have any.
No, is this weirder than that?
Maybe it's the same level of weirdness. Yeah, maybe this comment. There's a paper. It might have been by Kristen and Jordan. I don't remember.
I thought the resolution was supposed to be that, although it's true that in the S transform channel, the dominant contribution comes from the light operator. And that will be very tiny. Well, that will be essentially, that will be exactly factorized. There's a small contribution from operators still near the threshold. And so
that might be the
small,
case.
it's just
That might be the case. Yeah, like I said, this is there's a question mark here. So maybe the authors of that paper, whose names I don't remember, had some comments about. Okay, maybe one final comment. There are generalizations of this. So for example, I think maybe it was Herman asked a question about SL2Z black holes. One fun observation is that if you look at this torus cosmology, the T cycle shrank to 0 here, the phi cycle shrank to 0 here. If you think about the conformal structure of that torus, that means that as you go forward in time, the conformal structure of the torus is starting at tau equals 0 and it's going up to I infinity. This is a straight line, right? which is a geodesic with respect to the hyperbolic metric on the hyperbolic metric on the upper half plane. There are other cosmologies that are solutions of the equations of motion where you follow any other geodesic, on the upper half plane with respect to this metric. So those are other Big Bang, Big Crunch cosmologies. There are similar statements that one can make. In order to make statements about these kinds of cosmologies, you'll need to throw spin into the game. Okay, so I've just talked about the ADS-Schwarzschild black hole. If you looked at the Kerr ADS black hole, you would understand contributions related to this more general family of cosmologies. And of course, we could talk about statistics, not just of the density of states, but the other quantities in the conformal field theory, like the OBE coefficients. And these, I expect, are related to cosmologies where you have fancier topology, okay, instead of just a torus. These are closely related to the Euclidean wormholes that Maldacen and Maus wrote down some time ago.
Yeah, that's another question. I just wanted to make sure I understood the relation between the cosmology continued to something double cone and another geometry. So, I mean, at the level of the answer, I mean, so if you look at the torus wormhole, like the Cotler-Jensen computation, so that they were the function of tau.
Yeah, I think this is closely related. Yeah, okay.
So transform one side.
I think it's closely related.
And then you convolute it with the correct factor. Do you get exactly your middle guard?
No, this is something different. If you take the double cone and then you look at all possible SL2Z transformations on either side, I don't think you'll ever get a contribution involving these sort of intermediate states. This is a different kind of solution than, I think about the Cotler-Jensen solution as maybe a zero action, possibly slightly complexified solution of the equations of motion. It's basically the double cone. Cotler-Jensen solution is basically the double cone. One can do modular transformations, but I don't think you'll ever get a contribution in this regime. This is a new geometry. You come in on one side, you move into cosmology for one Hubble time or something like that, one ADS time, and then you exit with a different one.
But from the topologically, doesn't it sound? I mean, it's this. Isn't it, I mean, at least topologically, it's like you traded one cycle for the other's cycle.
Yeah. Yeah, I don't think we can. Let's talk about it afterwards.
Cotler and Jensen, they had this equation. They could have two different models. There could be
I understand.
a transformation between one side and the other.
I don't think as far. Maybe I'm okay. As far as I understand, it doesn't give a contribution of this type. We can talk
It's
about it
different stuff.
because Good. Okay.
Could you go further somehow with some other?
Well, I tried. So the Kontsevich-Siegel criterion means that you can never cross this line here or that line there. Yes. Good. Okay. Okay. Positive cosmological constant. This, of course, is the much more interesting and much more challenging case. So this is where you need to lower your standards, right? If you want to say anything interesting. Actually, that gets a laugh, but very dour today. Okay, good. So let's talk about, the prototypical solution of general relativity with a positive cosmological constant is de Sitter space. So here I'd like to consider the static patch of de Sitter space. So U, again, is going to be a radial coordinate that moves me in this way. I have a time coordinate that moves me up, and I have an angular coordinate phi. For those of you who haven't looked at de Sitter space for a while, this is a sketch of the Penrose diagram of de Sitter space. The static patch is the causal region associated to an observer. In our case, that observer is at U equals to 0. The full global slice is a two-dimensional sphere because we're in 2+1 dimensions. You can think of the observer as sitting at the north pole of that sphere. And that observer, of course, sees an event horizon, which in these coordinates is the place where the coefficient of dt squared shrinks to 0 size. So it's at U equals to pi over 2, right? And of course, time translation, the constant U slices are these sort of hyperboloids and time translation moves us along that slice. Good. And just as a reminder, in the static patch, there's a Hawking temperature, which in these units is just in units of the de Sitter radius. So L here was related to the cosmological constant. It's the de Sitter radius. It's equal to 2 pi or 2 pi times L if you're using units where L is not equal to 1. And what that means is that for perturbative fields, say for an observer sitting inside the static patch, they'll see a thermal density matrix, e to the minus beta de Sitter times h, right? Where h generates time translations, the Hamiltonian, the static patch Hamiltonian. And of course, that horizon has an entropy, which is a over 4g, which is L over g times some numerical factor. Okay, so what we want to try and compute, motivated by our earlier discussion, is something like trace of e to the I ht plus I theta j. Here, h is the Hamiltonian that generates time translations. J is the angular momentum that generates rotations in the phi circle. And I want to try and compute something which I'll call the trace over the Hilbert space of quantum gravity in the static patch. Now, I don't know whether that Hilbert space exists. I don't know whether I can really think of H and J as Hermitian operators acting on that Hilbert space. If that space exists, I don't know if it's a standard Hilbert space. I just want to see how far we can get. And I think I claim that you can get farther than you might think. Good. So first of all, what's one saddle point that might contribute to this partition function Z, which is essentially the Fourier transform of the spectrum of the static patch Hamiltonian? One saddle point that contributes should just be the original static patch, this geometry with my Lorentzian time coordinate periodically identified. And if I include a potential theta for my angular momentum generator J, then I need to do a periodic identification of T along with a twist in that phi coordinate. Again, that has the singularity. What should we do? You just saw the first half of my talk, and so I'm going to do the exact same thing. I'm going to consider a complexification of the metric, where now I take my radial coordinate to be some complex contour that depends on some real parameter rho, which is now the coordinate, the real coordinate of my space-time. And I'm going to think about complex contours in the U plane. Okay? So in terms of my static patch, that was U real. The origin was at U equals 0. The horizon is at U equals 2 pi over 2. And the contour that I want to consider is the one where I try and go just above this horizon. And indeed, there are other patches of this cosmology, okay? So if you analytically continue U, you'll find yourself in this patch up here. And what is that patch? That patch is again a torus times time cosmology, okay? So again, this is nearly the same formula that I wrote down earlier, where U is pi over 2 plus I rho. So this is a torus times time cosmology, where I have my T coordinate has now become a Euclidean coordinate, and my radial coordinate has become time-like. And this is in terms of the complex U plane, that's where our cosmology lies. So I'm going to consider a saddle point contribution to this partition function, which is not this singular geometry, but rather the one where I smooth out the singularity at the Milne, the Milne singularity at what was the cosmological horizon by taking a detour through this torus cosmology and going up to Scri plus. And near Scri plus, this geometry has a torus boundary, okay? I've done a quotient of three-dimensional de Sitter space. So Scri plus is no longer an S2, but it's an S2 quotiented by a conformal transformation in such a way that I get a torus. And the theta and t parameters, the angular potential and the periodicity of time in the static patch, now turn into the conformal structure of that boundary torus. And in the language of the wave function of the universe near Scri plus, that saddle point is viewed as a contribution to the wave function at Scri plus. And actually one can compute the action of it. It has zero action, but it has some non-zero one loop determinant. So, but I want to think about this in a slightly different way. Okay.
Is the action zero? Oh, maybe it's a technical question.
We can go through it if you want.
I mean,
There are boundary terms that one has to be a little careful about. I'm pretty sure we can talk about it afterwards. I have a.
so it's different from the action you would compute. I mean, if you have a boundary torus, you have what we call the Hamiltonian solution, which is some complex geometry.
This is one of those contributions which has zero action. There are other contributions that don't. Yes, okay, good. We're going to talk about them. Yes, okay, yeah. But let me motivate their existence, okay? So this is a complex solution.
Sorry to interrupt again.
Yeah.
Are these the same, essentially giving the same answer as what we would usually get from those Hamiltonian geometries, or different answer?
I think it is giving the same answer. I'm just interpreting it slightly differently. Yeah. I think so. But don't sue me for very much money if I'm wrong.
Okay.
Sue me for a little
But
bit.
no, I just.
Okay, yeah. Good, okay. So my boundary is a torus with t and phi cycles. And I have a geometry where the phi cycle is contracting. But, and this is the slight leap, maybe it's not so much of a leap, I don't know. The t and phi cycle should be treated democratically. Okay? So in particular, this wave function should only depend on the conformal structure at future infinity. So that means there's actually a full SL2Z worth of saddle points. Okay? And the way that I think about it to myself in the language of the static patch is that I described to you one way of resolving this Milne singularity at the horizon that I found when I periodically identified in Lorentzian time. But there's actually secretly a full SL2Z's worth of ways of doing it, related by these SL2Z transformations. And if you put that together, you would conclude that you should sum over. And when you do that, you get what I think you would probably call the Hartle-Hawking wave function at Scri plus. But now I'm going to interpret it in terms of the Hilbert space of this putative static patch Hilbert space. And I'm going to interpret this as a computation of the spectrum of the Hamiltonian and angular momentum generators acting on the Hilbert space of this quantum gravity in the static patch. And indeed, this formula, this formula has been written down before. This is the same as what you might call the pure gravity partition function in ADS3, DS3, but with a complex value of the central charge, up to some small piece, an imaginary value of the central charge. And now, importantly, with the identification of the conformal structure of the torus at Scri plus in terms of the periodicity in static patch time and angular potential. And of course, many people have thought about this previously, both in the context of ADS3 and DS3. But what I would like to advertise is that one can actually compute this Fourier transform of this explicitly and read off the spectrum of the static patch Hamiltonian. And Godet did a closely related computation over the summer. He wasn't thinking in terms of the static patch, and I think didn't interpret it that way. He was thinking only in terms of the Hartle-Hawking wave function. But now I would like to interpret this answer in terms of the Hamiltonian of the static patch. And let's just talk about the sector with zero angular momentum. So in particular, in that sector, I can compute the Fourier transform of the spectrum by doing that sum over Lorentzian saddle points. And I get an answer that looks like a sum of phases. And in particular, from this answer, I can read off the spectrum. And it has a couple of shocking features. First of all, it's a discrete spectrum. N and M are integers.
That's not discrete.
Yeah. Well, let's get to, yes. So it's a discretuum. We'll talk about that in a second. Yes. So it's quote unquote discrete. Okay. I have states at every rational value or square of a rational value of the energy. And I have degeneracies that are integers. Okay. Right. There are very few cases where you do a sum over geometries and you actually get integer degeneracies. So this is the thing that made me very excited. There are other contributions here, but they're all qualitatively the same. Integer degeneracies and energies with bounded real part. Yes.
Are some in -1?
Yeah. Okay, this is weird, right? Like you're supposed to be upset and start throwing tomatoes at me and stuff like
So you
that.
say there are some energies that are complex.
So yeah, so I didn't write them here because I was hoping to not have to talk about them. But there are energies. So these energies have a real part that's large. Well, these are real. Okay, there are other energies that have a real part plus order 1 complex part. I think they have to do with quasi-moments, but I'm not sure. Okay, so this is weird, right? The question, is it weird enough? Okay. So first of all, as was pointed out, we don't really have discrete spectrum. We have states at all positive rational values of the energy. And moreover, some of these states have positive norm and some of these states have negative norm. Okay. And let me tell you a little bit about those.
Sorry, it's the even states with negative norm usually contribute with a plus side to the trace.
By negative norm, I mean a -1 here.
Aren't they
It's not
fermionic?
negative.
Isn't that fermionic? Or-
Well, if I was computing something like trace -1 to the f, it would be a fermion. I'm not computing, to the best of my understanding, trace -1 to the f. Maybe there's an interpretation, and I'm welcome to discuss it where I am. But as far as I understand, I am not. And let me tell you why I'm okay with that interpretation. Yeah, this is the part where you're supposed to start getting angry at me. So all of this has been foretold. Good. So let me tell you a little bit about these things. So this function mu that's either plus or -1 is a famous number theory function known as the Mobius mu function. And it obeys a kind of quantum chaos. What do I mean by that? I mean that at large values of m, which is to say large denominators of the energies, remember the energies are rational numbers, right? These mu's are statistically indistinguishable from a random coin flip, okay? Modulo some number theoretic properties. So what that means is that although I have an infinite number of states that are arbitrarily closely spaced, when you actually calculate anything, most things cancel. So for example, if you were to calculate the trace of some function of h, you would get huge numbers of cancellations between all of the rational numbers with large denominators. And so actually, although you think you might get an infinite answer, you actually get finite answers. And here is where I want to make my pitch. So first of all, you might be worried about negative norms. But where do these negative norms appear? You have states, there's going to be some state with some particular rational value of the energy that has a minus sitting in front of its trace. It's a ghost, it's got a negative norm. And you would ask, well, can you actually see this? Can you actually see this, some non-unitarity arising from this in terms of physics in the static patch? But remember, an observer in the static patch can't live forever because of Hawking radiation. So that means that it's impossible to resolve arbitrarily small energy differences. So anything that you can observe is not going to involve a single energy eigenvalue, but rather some energy eigenvalues in some small window, okay? And the statistical properties of this mu guarantee that in any arbitrarily small window, there are going to be roughly equal number of positive and negative norms that cancel out with one another. And what I'd like to propose is that not only is this not bad, this is exactly what you should expect in de Sitter space. Whenever you have a perturbative field theory in de Sitter space, it has an infinite entropy. How are you ever going to get a finite entropy without a lot of, negative norm states to somehow get rid of that?
Sorry, why doesn't that argument apply to anti-de Sitter space?
I think if you're because you're inside the horizon. Okay, yeah.
So
not
what
even-
is this curly H? in Hilbert space?
Curly H is the putative Hilbert space of quantum gravity in the static patch of de Sitter space. It's not really a Hilbert space, right? It's a quote unquote, it's a Seiberg space, okay? It's a quote unquote Hilbert space where I'm allowing myself to have negative norms.
Well, as I said, it's not negative norm.
I'm not quite sure why you
It's
say
more
that.
like negative probability.
Negative probability.
That's not negative norm.
Negative probability. Is that-
Negative norm contributes with a plus.
Okay,
As a mnemonic, think of the traces contracting the method with lower and upper
yeah,
indices.
okay, I'm using, it's negative probability, sorry, I'm using,
There's
I'm
no
probably using.
interpretation in Hilbert space that things act.
It's not a Hilbert space, it's not a Hilbert
So
space.
what are you tracing over?
I don't know, I'm computing a spectrum, okay. Yeah, I haven't given you a direct construction of this Hilbert space. I've given you a computation of something that I would call trace of
But you
Edelman
would
space.
ask, does the system have any sensible Hilbert space?
I don't think it has a sensible Hilbert space in the usual sense of quantum mechanics, okay? Nor do I necessarily think that we should expect that if you were trying to describe de Sitter, the physics of the static patch of de Sitter space, that you would expect that it should. Yeah, negative probability is probably a better way of saying it than negative norm.
But that was wrong, I think, on my part.
Okay, well, maybe you can coach me on the exact right language to use, but in any case, we have negative coefficients appearing in this putative quote unquote Seiberg space trace.
Sorry, so the mu is a function of m, but at which m it takes a value of +1 or -1.
Right, so you go on Wikipedia
Oh,
and you look up the definition of the Mobius mu function. It's ±1, depending, so it's 0 if m, the prime factorization of m has any squares, and it's
Oh.
+or -1 depending on whether it has an even or an odd number of prime factors. So it's some number theory thing.
oh,
Good, okay, but here's the reason you might want to try and take this seriously, which is that, these -1s and +1s cancel against each other in the computations of observables, okay? So I could take that spectrum along with those mu's, and I could go ahead and compute what you would call the finite temperature partition function. Sorry, there shouldn't be a ds there. You can just compute the finite temperature partition function and then extract the entropy. And if you set the temperature equal to the de Sitter temperature, you get A over 4G, including this numerical coefficient.
If the temperature is not equal to the de Sitter temperature, does it still have some other interpretation?
Probably, but I haven't really thought about it. Yeah,
But you get the finite answer in both cases.
yeah, I believe you get a finite answer. I would like to give you a plot of it, but that's why this is to appear rather than has appeared. Okay, let me make one final comment. I'm out of time, which is that this is not new. So in particular, back in the olden days when dinosaurs roamed the earth, and I was a graduate student, people worked on DSCFT. And one of the observations that appeared in the literature, this is not my first paper, but my first good paper, okay, was that if you took Cardy's formula for a 2D CFT and you just computed it at beta equals to 2 pi, you got the de Sitter entropy, okay? And this was viewed as numerology, okay? And indeed, this paper that was my first pretty good paper, it had a couple of mistakes in it, okay? Among other things, we didn't know about this factor of I because we normalized our stress tensor with the wrong sign, okay? If you normalize your stress tensor with the wrong sign so that the stress tensor 2-point function is related to the coefficient in the graviton wave function. And if you normalize it with the sign, the wrong sign, then you get a real central charge. But if you normalize it with the sign where the wave function is a right sign Gaussian instead of wrong sign Gaussian, something I learned from Juan's paper, then you actually get an I here. Okay, so we missed that factor of I, and we also missed that factor of I. Okay, so we made a numerological observation where we missed two factors of I that happen to cancel against each other. But now I claim that we've resolved those factors of I. Okay. The actual central charge with the correctly normalized stress tensor is purely imaginary, mostly imaginary. And what we call the CFT temperature, right? So the CFT lives up here, okay? And the CFT temperature is the thing that's conjugate to a Euclidean translation of scribe plus. But the correct thing we're interested in is this Lorentzian guy here, which means that you're really taking Cardy's formula with an imaginary value of the central charge and analytically continuing the temperature. And so I think that is one way of understanding the success of this calculation. Okay, I've gone a few minutes over, so I'll just conclude. I've described here two somewhat speculative avenues to the study of 2+1 quantum cosmology. One, when lambda is less than 0, we've related a closed Big Brunch universe, Big Bang, Big Crunch. Okay, I hereby say that Big Bang, Big Crunch cosmologies are now Big Brunch cosmologies. Okay. The Big Brunch cosmology is related to a 2-point function, the spectrum of some conformal field theory. And I described a proposed formula for the spectrum of the static patch Hamiltonian, which appears to reproduce the DS3 entropy. But of course, many questions remain, some of which I've written down here. I mean, I think one of the things I'd really like to understand is the relationship with other approaches to physics and de Sitter space. Right now, I haven't thought about that too much, but that's something that I'd like to understand better. Thank you. I'll make one more. Oh, sorry. I should let other people ask questions.
Can you make this last comment you want?
So Herman has a question. Okay, so the other thing I was going to say is like, I think this is great, right? But really, I'm getting it one way, like we went through this avenue, I described this through this avenue of computing a spectrum with, energies and some plus and minus coefficients. But I got it through a sum over geometries, okay? And it shouldn't necessarily surprise you that I can get the de Sitter entropy from a sum over geometries. In Euclidean signature, we're used to doing that all the time, right? The sphere partition function is the exponential of the entropy. Okay, so it shouldn't necessarily surprise you that in a calculation that I did with a sum over geometries, I could get the de Sitter entropy. I think the nice thing is that we now have a spectrum to play with, but I would love to understand better the relationship with these Euclidean approaches. I mean, I think morally speaking, we're doing a sum over lens spaces and Euclidean signature, but I don't have anything terribly useful to say. Yeah.
Is there still sort of a dominant saddle point here?
Yes.
Analogous to
The dominant saddle point, that is to say that
vacuum character or something.
I don't know if there's something analogous to a vacuum character. The one that gave me the de Sitter entropy is in the language of this SL2Z family, the S dual of this.
Correct, so similar to, so it is sort of the as dual.
Yeah.
Some kind of fact. But in the one of the disciples, practical, which one?
It's the, so this is the one where phi. Yeah, this is the one where phi is contractible. Okay, it's the one where T is contractible that gives you the de Sitter entropy. There's probably
It's not obviously related to the sphere because
it's not obvious. It's not obviously related to the sphere, but probably if you thought about it enough, it would be obvious. I guess if you have to think about it a lot, it's not obvious, but there's probably a way of thinking about it. I strongly suspect we could relate this to Euclidean stuff. But I think the advantage is that there's a real like, I don't necessarily want to think about it in that language, but you probably could.
One spaces are what defaults of S3.
Yeah, so the reason, I had a paper with Castro and Lashkari a while back where we tried to do this, but basically the idea is that if I take, okay, one way, okay, S3, one way of thinking about S3 is that you take the inside of a donut and you glue it onto the outside of a donut, okay? That's S3, that's a saddle point of Euclidean signature general relativity with positive cosmological constant. I could also take the inside of a solid donut and glue it to the outside of a solid donut. That is, say, glue two solid donuts together with any SL2Z transformation. That gives you a lens space. And so that means that the sum over those saddle points is a sum over SL2Z. Now, it's not actually the same sum that I wrote down earlier, because one of the cycle, this cycle is contractible, okay? So that means I actually get a sum over SL2Z mod Z. But then this cycle is contractible on the outside, which means that you actually get a sum over a double coset, SL2Z mod Z mod Z. Whereas previously I only had a sum over SL2Z mod Z. So here are the words that I want to say, and then you can tell me how to make those words precise. The words that I want to say are, there's an observer sitting, on one of these, and I'm not allowed to contract the cycle that would murder the observer, okay? And so I actually only get one sum over SL2Z mod Z. So that's how I think the story should go, but I don't have anything more than words to say.
If you start with Hardy formula of the previous paper result, will you also get a similar spectrum if you library do that
We were
continuation?
thinking, this was back.
Yeah.
So I think the correct interpretation of all that DSCFT literature is in terms of the wave function at Scri plus.
Yeah.
And essentially what I'm trying to do here is reinterpret all of that in the language of the static patch.
Okay.
And so,
So that means this result.
yeah.
If you universe
back in the olden days, we weren't computing things like this. Well, I wasn't computing. Okay, you were computing things like that. I wasn't computing things like this, and so the original DSCFT program, at least in my interpretation, was a study of the wave function of the universe at Scri plus and interpreting that wave function in terms of the correlators of some putative boundary conformal field theory. But nobody knew what that conformal field theory was, or even necessarily exactly what properties it should have. This, I think, is a different kind of calculation, right? Just trying to do a pure gravity calculation and then noticing that actually it had all of the elements for it were there in those old formulas.
Yeah, but
that wasn't what.
But to the partition function level, so does one you derive in this kind of the whole business equal to the result from the Cardi formula for 2D circuits?
Well,
The partition function.
I mean, it's a little bit like the Cardi formula, but reinterpreted. It's like Cardi formula evaluated at an imaginary.
Yeah. Like after all the and then the continuation of the Cardi formula, you get the same Cardi function.
This spectrum is literally what you get if you take the so-called pure gravity partition function in ADS3 that Edward and I computed in 2007, and you do two unusual things. You take a complex value of the central charge, and instead of computing the Legendre transform, you compute the Fourier transform. Yeah.
The spectrum doesn't look terribly chaotic to me, and
Yes, okay, the spectrum of energy levels is not chaotic. This is first of all, this is a pure gravity thing.
Yeah.
And, okay, I don't know, okay.
Does the mu save you in some sense?
The mu's are chaotic in this sense.
Yeah, I'm just when it's
So that's the sense in which it's chaotic, right? You know, they obey a sort of quantum. So this phrase arithmetic quantum chaos means that you have some of the features of quantum chaos, but not all of the features of quantum chaos. That's one lower thing of interpreting. Yeah.
So, if I understood correctly, some of their energies are small. Does that mean that? Dark doesn't mean that you have some things that look like point particles inside.
Good. Yeah, maybe you should think about this as point. Yeah, they certainly look like conical defects, right? Yeah. Okay, good.
But isn't this like? It's a little funny because we started with a theory which didn't have these particles.
Yeah, yeah, I'm not sure exactly how to interpret that. Yeah.
The mu does not depend on n, but do you have a
Mu
some?
does not depend on n. This is just, that's correct.
Yeah.
That's correct.
Why? Is any?
It's the answer you give.
Oh. So it's like if there is a so what is like n Babel's kind of family
Yeah,
or?
that's right.
Okay.
That's right.
Is the energies in the static mass being the same thing as taking the S2Z sum and expanding it on the basis of torus characters, or is it? In other words, if I take that answer and I expanded it in terms of the torus characters in a given channel.
No, I mean, it's important, it's important that I'm taking a Fourier transform, right?
But I think I'm a little confused. I mean, if you go back to the previous.
Yeah, I mean, like, this is like, I'm doing this. And then I'm just expanding like this.
You're literally expanding like that, but you're not including the whole kind of block, which is the sentence.
There's also a block out. This is, oh, sorry, maybe I can answer it this way. This is the analog of the primary state partition function. Yeah, sorry, okay.
So
There's
those are, there's
there's
an
an-
expansion in terms of the character.
Yeah, this is an overall factor of that eta function thing.
But that thing could be projected out if you
Yeah,
change the Viridor.
Then
Okay, I need to unpack that sentence, but
A priori, yeah.
yeah.
I mean, the parameter T is directly one of the moduli of the torus
Correct.
that I plus.
Correct.
I just thinking that way. Yeah.
But I have to take it to be purely imaginary. Sorry, no.
It's a function.
No,
of the-
yeah.
Doesn't matter. But also, so the energies you have are, they correspond to like, dimension of the operator pure imaginary, not shift by one. Oh, some of them, sorry, some of them are just in different places in the complex one. Is that right? The ones you didn't write?
Well, they have a small imaginary part, which would mean a real contribution.
The small, the order one over G.
Not order 1 of G.
Are the measuring parts positive?
I think it can have either sign. If I remember, I believe it can have either sign. But I don't sue me for much money. Okay. Okay, any other?
If there are no more questions, let's thank Alex again.